We go. Hi guys, welcome. Good to have you. I'm sorry we can't be together right now. Hopefully, with the weather getting better, I'll see you very soon. Okay, today I'm going to tell you about loss functions. And basically, loss functions are the fundamental feature of any learning system. What it's trying to do is optimize some function. And if you have some data made up of things that have inputs and labels X and Y, a loss function gives you something to minimize. And you define it as some expected value, which is an average of a function called loss, which is the difference between what the label is and what you predicted, y and y hat. And loss functions mathematically, of course, are things that we're going to be optimizing, but there's the equivalent way of thinking about it in the brain as well. So, learning systems in the brain rely on loss functions. So, it's thought that dopamine is signaling things that have to do with reward prediction errors, which is the difference between the reward associated with something and what you actually received, what you predicted about that reward and what you actually received. And then this is dopamine is the teaching system for a part of the brain called the basal ganglia, the striatum part of the basal ganglia. And in another learning system, um, in the cerebellum, climbing fibers is a sensory prediction error. So this is making predictions about uh, sensory things like position of things, movement that you made, feeling that you had, not the reward associated with it, but the sensation of the action itself. And so there may be these two different ways of transmitting errors in observation minus prediction to the brain. So they both rely on this concept of a loss function. And so I'm going to tell you about loss functions today and concepts of minimizing them. Um, and I'll also tell you a little bit about, because we're going to be using derivatives, which are gradients of functions. I'm going to tell you a little bit about the origin of derivatives and the discovery of them by Newton and Leibniz in the 17th century. So let's begin. And unfortunately, I can't see you. So if you have any questions, I don't know. Just go ahead and say, Reza, I have something. Just go ahead and break into it, and I'll be happy to, of course, um, answer it for you. Okay, so a typical problem in a loss function begins with, let's say, regression. So regression is is a problem where you are trying to estimate something, y hat, as a function of some variables. Y hat is a function of some variables w that you're trying to estimate and some input x that you've been given. And if it's linear regression, then your y hat is w0 plus w1x plus w2 x2, so forth, if x is a vector that you've been given. So it's something like W transpose X. So we can write that as the problem that we're trying to solve. And I can give you an example of it. Let's say from genetics. Suppose that your Y hat is onset age for, let's say, Huntington's disease. Suppose you want to predict that based on some genetic profile that you have from some individual, when they're likely to, or if they're going to get Huntington's disease. So what you do is that you take the some data from them that includes things like current age. There's a component of the genome called CAG, which is you can look at the number of repeats that there are of those. basically the more of these repeats they are in a row, CAG, 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 the more it repeats, the more likely it is that it can result in eventually Huntington's disease. X3 might be something like, did the mother have HD? So this familial information, and X4 could be for the father, and so forth. So you could have some variables that describe things that you think are important for making the prediction, and then your output Y hat might be something that says this is the predicted onset age for HT. So then you're going to train this simple linear model, and we're going to use a loss function in this case. So the difference between what I predicted, Y hat, and what I observed, Y, I'm going to write it simply in this case as the squared error. So this is the error, and we're going to square it, and that's going to be our loss function. Now, in principle, of course, loss function can be anything. For example, you might want to make certain losses more important than other losses. If you imagine this landscape of losses, you might have, it's not just a quadratic function, but something that says, this kind of loss means more to me than that kind of loss. But in this case, it is viewing all losses the same in the sense that it's just squaring it. It's our simplest form. So the expected value of loss, which is what we're going to minimize, is simply you take all the data that you have and you sum it over all your errors. So this is a typical loss function that you'd want to minimize. And so let me give you some ideas about characteristics of these errors and what you might expect as you minimize loss functions. So suppose let's take the simplest model, simplest regression model. So it would look like this. So we just have one variable X, and we're making predictions Y, and we have two parameters, W0 and W1. So then my loss is over my data set squared. So that's my loss. This is a quadratic function. Suppose I have found the minimum, meaning that I've minimized this function. Now, if I've done it, so I have this W0 and W1. You can think about it as a two-dimensional surface here, and on top of it is my loss. Here's loss, and I've found some minimum here at the bottom here, and if I found this minimum, then at the minimum, then it doesn't have to be a global minimum. It could be a local minimum. In this case, it would be a global minimum since it's just a quadratic function. But if I found some minimum, then at that minimum, let's call W star, at that minimum, some things must be true. And one of the important things that must be true is that the derivative of this loss with respect to W should be zero. So because we're at the minimum of this function. So that means that the derivative of the loss with respect to, let's say, W0, what is that going to be? Well, I have the sum here. So sum of something raised to, each element is raised to a power of 2. The derivative is going to be 2 over n sum. What's inside the parentheses times the derivative of what's inside the parentheses with respect to W0, which is -1. So that's the derivative of my loss with respect to W0. It's a sum. And when you look at this, you notice, oh, okay, this is just my error, Y tilde of I. So that was the error that I made in predicting the output. So what I'm doing is I'm multiplying each of the errors times a -1 in this case, and I'm summing it up. And that has to be this sum here with respect to W0, it must be equal to 0. So actually, let me move this. So this has to be 0 because I'm at the bottom of this quadratic, this loss function, right? Because I found the W0. So if that's true, then what I have is that minus 2 over n times sum of my errors, each of my errors is equal to 0. So what this says is that the sum of my errors must be 0. So when you do any kind of fitting, at the end of the fit, you should look at the errors that you have and sum it all up. It has to be equal to 0. Otherwise, you didn't find the correct solution. Which also says that the average value of the errors must be 0. So if you were to plot your errors as a function of x, you should see that it has a mean 0. So if this is x, and I'm plotting my errors, it should have a mean 0 around it. So that's the first property of my loss function. After I find a solution, W, to my regression problem, if I look at my errors, it should be mean 0. There's another thing that we can understand about it. If we take the derivative now, take the derivative of the loss with respect to W1, the second parameter. And what I'm going to show you is that after you find the solution to your problem, if you look at the parameter, in this case W1, you should find no trend in W1, no linear trend. I'm fitting a linear function, so W1 is multiplying X. So after I find W1, if I now look at the errors associated with my data as a function of X, I should have no trend that is linear because I've accounted for the linear relationship. So let me show you how that can be. So let's find the derivative of loss with respect to W1. So I'm going to find the derivative of this equation. Oops, sorry. I'm going to find the derivative of this equation with respect to W1. So let's see what that's going to be. So I have 1 over n times the sum of something squared. So the derivative of that is going to be 2 over n times the sum. What's inside the parentheses? And now the derivative of what's inside the parentheses with respect to W1, which is minus xi. That has to be 0. That sum has to be 0 because I've reached the bottom of my loss function. And again, this is error. So this is equal to 2 over n sum of my error on every trial times minus xi. This has to be 0. So what this means is that my error cannot be equal to some linear function k times xi. If that was the case, if there was some linear function of k, if my errors could be represented as k times xi, then of course that sum would not be 0 because you're multiplying x by itself, you get a squared. What this means is that if you look at your errors as a function of x, because you're fitting a linear function, you cannot have something that is a linear, something like this. Obviously, its mean isn't 0, and there's a linear relationship. However, it is possible for you, if you were to plot your errors as a function of x, you might see something like this. So this is not a linear function, and its mean is 0. It's just some nonlinear function, which says that basically there was some nonlinear relationship in your data that you didn't account for. So this is possible, this latter case here. This is possible. This means there was an error in your fit. Okay, let me stop for a second. See, do you have any questions about this so far?
Could you explain again how you determine like if there's an error in your fitting just based on the plot?
Yeah, so two things that I just showed you. So first, look at the errors. Why tildes? The sum of them have to be 0, which means the mean of your errors after you're fitting it should be 0. And second, whatever model you're fitting, linear model, nonlinear model, however it is, if you look at the errors should not have a component of the model in it. So if you're fitting a sinusoid, let's say, when you look at your errors, you shouldn't have a sinusoid left. If you're fitting a linear model, you shouldn't have a line left. Does that make sense?
Yes, it does. Thank you.
Okay, my pleasure. Okay, now typically, if one wants to fit these kinds of functions, one can use linear algebra and solve the problem in a single shot. So let me show you how that would work. Suppose you have a vector y hat. This is your estimates that you're making. And we're going to put together our estimates from the first data point to the last data point in this vector like this. So my y hat looks like this, and x now is going to be a matrix. So x is going to be something that looks like this. There's going to be a 1, there's going to be x1, x2, x3, so forth. And maybe there's d elements in this x vector. So I'm going to build a model that's going to associate a vector x with a scalar y hat, and there will be a vector w that is going to map those x's to y's. So my x's are shown here. So I have a bias w0 that's going to multiply by 1. Then w1 is going to multiply by x1 and so forth until I get to xd. And then I have a second data point. So another data point here, x1, second data point. So if I were to write this in a matrix form, I will get y hat is equal to this matrix x times this vector w, where y hat is an n by 1 vector, x is an n it's going to be an n by d plus 1. D plus 1 is the size of the number of columns, and w is a d plus 1 by 1 vector. So it's just a vector that has, d plus 1, meaning because of the w0, the size of it. So this is my linear problem. I want to find w, and how would I do it? And we're going to use the loss function for this as well. So what is my loss? My loss is sum of the squared errors, which means the expected value of something. So that's going to be 1 over n. Let's call my loss j. So j is going to be 1 over n, the number of data points that I have, y minus xw transpose y minus xw. So y minus xw is my error. It's a vector of errors. And what I'm doing is that I'm squaring the vector of errors, and then I'm summing it up, and then I'm dividing it by the number of data points, 1 over n, which is the expected value of my error. Does this make sense? This way of writing down the loss function?
Yes.
Okay, so just to remind you, so this is the vector of errors that's getting squared, summed up, divided by n. Okay. All right, so I want to minimize. I want to find the w that minimizes my squared error. So let's just multiply these out. Okay, so I just multiply these through. That's my loss function. Of course, j is just a number. It's just a scalar value, right? Because what I'm doing is that I'm taking my errors and I am squaring each of my errors, and then I'm adding them all up, dividing it by the 1 over n, the data point. So it's just the final thing is just a number. So that means that this quantity here, this quantity here, this quantity here, this quantity here, this quantity, each of them is just a scalar. I'm most interested in the two ones in the middle because oh, I actually screwed this up here. Did I do that? X, Y. Yeah. So I made a mistake here. So this is Y transpose XW. So, okay, so that my whole point here was that because this is a scalar, this I can write it as a transpose of itself, which means so that's equal to okay. So this is our loss function. So we want to minimize this loss function. So what I do is that I find the derivative of J with respect to W. So remember, W is a vector. When I take the derivative of a scalar, so what I'm doing is that I'm taking the derivative of this equation first with respect to W0, then with respect to W1, then with respect to W2, so forth, until I get to the bottom, WD. Each time I take a derivative, I'm finding some function. And so I end up with a row by row definition of my function. So this is a vector of size W. So whatever is the size of W, in this case, D plus one vector. So let's find the derivative of this function. So it's important to realize the size of this function that you're computing, the size of this vector, because when we take the derivatives, you're going to need that to know whether you should take the transpose of something or not. In particular, of concern is going to be this term here, because you have a linear function that has a vector W in it. You're going to take the derivative with respect to W, and the question is the final result, what is that final result going to be? And then we're going to be able to check it by knowing the size of these matrices. Okay, so let's take the derivative with respect to W. So there's 1 over n here. The first term, Y transpose Y, doesn't have any W's in it, so we don't need to worry about it. The second term has a minus 2, and if I take the derivative with respect to W, I'm gonna claim that derivative is X transpose Y, and you should ask, okay, does that make sense? Does that provide the correct dimensions for it? So dj dw is a vector of size n d plus 1 by 1. That's the size of W, right? So it's D plus 1 elements in it, and it's a vector, so it's by 1. So X transpose, what was X? So here's X. Look at its dimensions. N by D plus 1. So the transpose of that is D plus 1 by N. What's Y? N by 1. So that gives us the right dimensions. Plus the second term, W transpose X transpose XW. So here W appears twice. So this is a quadratic function in W. The derivative of this with respect to W is going to have, just like a quadratic function, you're going to have a 2 in front of it. And then you're going to get X transpose XW. And again, let's check to see if we got the dimensions right. So X transpose, what is X? Look at X here. So transpose of that is D plus 1 by N. Multiply by X, I get a D plus 1 by D plus 1. And then I multiply it by W, which is a D plus 1 by N. So that also gives me the right size at the end. So my point about this little exercise was that when you take derivatives of scalar functions that are dependent on vectors, the way to make sure that you found the derivative correctly is to check the dimensions of each of the elements that make up that vector. Okay, so if we have found the correct derivative, then at the solution that we're seeking, this is equal to 0, right? Because that's the bottom of the hill. And at the bottom of the hill, the derivative with respect to the parameters, W, is 0. So now we just solve this equation. We get minus 2, or let me do it the other way. So we get 2, 1 over n. Well, we can get rid of 1 over n since we don't need it. Transpose x W is equal to 2x transpose y, which means W is equal to x transpose x minus 1 x transpose y. So that's a solution to our linear problem. This is called the normal equation. And it's related to a concept in linear algebra called the pseudo-inverse. So the pseudo-inverse, let me put a star on top of this rectangular matrix X, is defined as this term x transpose x minus 1 x transpose. So that's the pseudo-inverse of the rectangular matrix X that gives us the solution to this normal equation. Okay. Why is it called the pseudo-inverse? Because x star x times W is equal to x star y. So it's finding the pseudo-inverse of our of the rectangular matrix X. Okay. Any questions? Any questions about this? So this is the way to find the inverse of a rectangular matrix. And we found how to find the derivatives of linear functions that depend on vectors and matrices. So how do you know the model that you should use? So let me use an example to show you something called cross-validation. Suppose that you're wondering, should I have a model y hat is equal to W0, W1x, or should I have a model like this, or should I have a model like this? Which is better? Obviously, as I add these polynomials, what I'm doing is I'm increasing the complexity of my problem. And the idea is that as complexity increases, your fitting will get better, but there's a danger of overfitting. So how can I test for this, that I'm not overfitting it? And the idea is as follows. Suppose you had some data points. Something like this. And you fit your model to it. Suppose that you fit a linear model. So it would look like this. But now suppose that you fit a quadratic model. Now you're going to get something that's a little bit closer to your data, like this. If you fit a quadratic model to it, right? And if you fit a cubic model, it would even be more wiggly, if you will. So that's going to reduce your errors for sure. But how do you know? Is there a way to quantify this concept of overfitting? And the idea is that imagine if you had made your fit with the linear function and you take a data point and take it out of the training set. So suppose that if I were to take this data point here and not use it in my training set, well, it's not going to change the linear function very much, right? So if I now were to fit it now, maybe it will, maybe it will look like that. It's not going to change it very much. But if I were to fit that function for my cubic polynomial, it's going to make it so that this doesn't go. It will probably go down like this. So it's going to change it a lot. So if I were to train without one of these data points, and if I have a very complicated model, it's going to make a big difference in what it's going to predict for that data point that I did not train it on. But for a simple model, it's not going to change it very much. So of the idea behind cross-validation is to have an estimate of how much error do you get if you were to leave a data point out, and quantifying that as a function of your complexity of the model. So it goes like this. So cross-validation. So you first fit all of the data except one. Next, what you do is you measure error at the test data point. So the one you left out. So now you measure the error. So, the error for the white one is going to be this. Error for the red one is going to be less. Then what you do is that you repeat over all data points. So you leave one out, you measure the error, you leave another one, you measure the error, and so forth. And this is called the cross-validation error. On each data point, you're measuring the cross-validation over error, and you find the expected value of your cross-validation error, which means the average cross-validation over all data points. Now, if you were to plot your loss function as a function of your complexity, model complexity, obviously, as model complexity increases, your loss functions are going to decline. But at the same time, if you were to plot on this axis here, cross-validation, the expected value, you might see something that has a knee, something that has a minimum, meaning that as you begin to overfit, then the cross-validation error would increase. And the idea is that that's how you might be able to tell the correct order for your model. Let me stop for a second, see if you have any questions.
In in some science approaches, they leave out several values, not just one. Is there a reason why you may choose one or the other?
The idea is basically find the expected value over the data that you've left out. So it's if you leave several, then you're getting more of an average over a neighborhood, which is just the same idea, just scaled up a little bit. Okay. Now let's continue. And now let's get to describing if we're going to use the gradients, which is, what these derivatives are telling us gradients. And we want to have a sense of the step size that we should take. How big of a step size is too big when we are trying to minimize such functions? And what I want to show you is that in principle, we can estimate exactly the maximum step size that we should take when we are attempting to, learn from an error, at least in the case where we have a linear regression model. So let's try to understand the maximum step size and get a sense of a learning system that will move some fraction of the maximum permitted step size. So the algorithm that I'm going to show you now is called LMS. And we're going to show you how to do this using geometric approach. So we have a simple model again. So we have y hat is W transpose X. So we have two vectors. So this is very similar now to what we had with perceptron, except that our X's aren't, the y hats are not the sign of y hat, but just the actual y hat itself. So if you remember, what we did is that we said that in some space, we have this vector x, and we have some vector w. And if we project w onto x, we have something that's related to the w transpose x. So w transpose x is magnitude of w times magnitude of x times cosine of the angle between w and x. And so what I'm interested in is knowing is that, well, how much should I change w so that I can, get the correct answer when I do w transpose x. But if you think about it, well, obviously you want to change w by some amount delta here, so that when w plus delta is used, you can, cancel out the error that you have. So this equation here tells us that cosine of alpha is w transpose x divided by the magnitude of w and x. So if I were to project now w onto x, I get some scalar value. Let's call that rho. And this rho is, if you use trigonometry, this is just w times cosine of alpha, which I can now replace cosine of alpha with what I just wrote. So I get w transpose x times magnitude of w divided by the magnitude of w and magnitude of x, which gives me w transpose x divided by the magnitude of x. Well, w transpose x is just y hat. This is what I'm estimating, times x. Sorry, divided by the magnitude of x. So this is what my model is telling me. What is it that I want? Y. I want y, not y hat. And so what I want to do is change delta by an amount that is going to take me from where I am to completely cancel the error. So what I want to do is add to w some amount, and that amount is going to be the difference between y and y hat. That's my error, and it should be in the direction of x. So here's a unit vector in direction of x. So this is my error. This is a unit vector. I'm taking my error, I'm multiplying by a unit vector in direction of x, and I'm going to add it to my vector w. And when I do that, I'm going to be able to cancel this error. So what is this quantity? That is y minus y hat. This is my error divided by magnitude of x squared times x. Okay, so what this tells me is that when I want to change w, what I should do is add to it something. If I want to change w so that it completely cancels the error, then I should add to it something that is this amount, y minus y hat divided by the norm of x, the magnitude of x squared, times the value of x itself. So this is a vector, x is a vector. Its magnitude squared is going to be what I'm dividing by my error by. So if I did that, I will completely cancel the error. Usually you don't want to move that far. So you put an eta in front of it, where eta is now going to be less than or equal to 1. So this tells us that, look, if you wanted to know how much you should learn from error, the maximum you should learn is the quantity x divided by magnitude of x squared times the error. Usually you want to learn some fraction of that. So you put an eta in front of it that says I should learn a little bit less than my error. This is called LMS. This equation is the LMS out, which is basically telling you the gradient of what you should the amount that you should change on each trial in order to reduce the error by updating your W from one trial to the next. So okay, so this gives us an example of how to do trial by trial learning. What does this have to do with this function that I wrote up here? So LMS algorithm gives you something, and then look at this W here. I wrote this function up here. I said, this is the solution you want. So what does this function here have to do with this W here that I find at the end of my learning? Can I show that if I were to learn like this, I will eventually get to the bottom, and the bottom will give me a W that looks like the normal equation? That's the next topic that I want to show you how to prove that. And this is the steepest descent. So what I want to show you now is that if you learn using the gradient of the error, which is y minus y hat, you can times x, that you can end up with the normal equation. So here's so our typical function that we're trying to minimize. Our loss is this. So this is the squared error, and we can find the derivative of this loss. This is the gradient of the loss. So this is the derivative of j with respect to w. Remember, this is a vector now, and this is going to be, we did it a couple of pages ago. It's something like this, which is 1 over n times 2 times x transpose xw minus y. Okay, so this is my gradient. Now, as you know, in calculus, the gradient is a vector that points toward an increasing slope. Now, what I want is to move in the opposite direction. So I want to reduce my loss, not increase my loss. So what that means is that I want to have a learning that says W in, let's say, trial 1 is W at trial 0 plus eta times minus the derivative with respect to W, right? Because I want to move opposite to the gradient. Remember, gradient points in the direction of increasing value. I want to move in opposite direction. So what that means is that my learning rule is going to be eta times x transpose y minus xw. So the negative of the j with respect to it. So this is error, y tilde, right? Difference between the teacher, y, and my estimate, xw. Okay, so this is my LMS learning algorithm. This is my trial by trial learning algorithm. And what I want to know is that if I were to learn like this, can you show me that at the end of my learning, I'm going to end up with the normal equation that I had? And that's what I want to show you now. So let's walk through this slowly. So W1 is W0 plus eta x transpose y minus x W0. So I start with W0. I have some guess of my weights. I find the difference between my observation y and my prediction x W0. I use this equation to update my W's. So let's simplify this. Let's bring together some of the terms. So let's bring together W0s. I get this identity matrix minus eta x transpose x times W0 plus eta x transpose y. Okay, so that's my W1. So W2 is W1 plus eta x transpose y minus x W1, which is I minus eta x transpose x W1 plus eta x transpose y. which I'm going to now put W1 from the equation above. So I get I minus eta x transpose x. And now I have this W1 that I'm going to put there. So that's W2 written in terms of W0. Okay, so we can simplify this. I get the first term is going to be this quantity that's going to be squared times W0 plus now, if you look at this, what you see is that there's this quantity eta x transpose y times 1. Then you have eta x transpose y times something, I minus eta x transpose x. And then there's this quantity here that's being raised to a power 2. So in general, if I were to do this for W3, for example, for W4, what I would see is that W2 is equal to a sum of I is equal to 1 to 2 I minus eta x transpose x raised to the power of I minus 1 times eta x transpose y plus I minus eta x transpose x squared times W0. So what I did is that I took this and I wrote it as this. And then what remained is that first term. Okay, so if I were to keep doing this, then I get this W infinity is equal to this sum of I is equal to 1 to infinity of I minus eta x transpose x, I minus 1 eta x transpose y, plus this term raised to infinity W0. So this is the end of my story. When I get to the end of my learning, this is the equation that I have. So how can you show me that this is the normal equation? I mean, can you prove to me that at the end of my learning, I get to my normal equation? Now, what's interesting about this equation is that you're raising something to this power and then you're adding it. And the term that's used to refer to this is a geometric series. So I'm going to show you how do you find solutions to geometric series. So let's begin with a scalar. Suppose instead of these matrices that are being raised to powers, suppose I just had a scalar. Suppose I had a sum of I is equal to 1 to n of a scalar a raised to the power of I minus 1. Suppose I wanted you to tell me, does this thing, what is this? What is the sum of this a raised to the power of I minus 1? This is called a geometric series. So how do I find that? Well, what does this mean? That means a is raised to the power I minus 1. But I is 1, a is raised to the power of 0, plus a raised to the power of 1, plus a raised squared, plus a raised to the power of I minus 1. So if I were to sum this up, I get something. Let's call that S. And I'm going to put a little n underneath it because I have n elements that I use to sum. So the sum, I'm going to call it Sn. I want to find what is Sn. Well, what I can do is multiply this sum by a. See what that does. So now that's just a times Sn, which is equal to, well, a to the power of 0 just becomes a plus a squared plus blah, 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 plus a I. And that's some I'm going to call a times Sn. So now what we're going to do is take Sn and subtract from it a times Sn. So take the first equation, subtract from it the second equation. So when you do that, what do you get? The first term here stays, a0 stays. The second term, a1, gets canceled. a2 A squared gets canceled all the way to the end, and the only terms that remains at the end is a to the power of n. So that's 1 minus a to the power of n. So now solve for a. So now I get the sum that I wanted. Okay, so that's the sum of my geometric series. So I have a geometric series. I can find the sum by this equation. Okay, so this means that as n goes to infinity, the sum, let me write it down below. So as n goes to infinity, the sum of a I minus 1, which is equal to 1 minus a to the n, 1 minus a, as n goes to infinity, this sum, what happens to it? It goes to 1 over 1 minus a if a is less than 1. So the sum is going to converge, and it's going to converge to 1 over 1 minus a if a is less than 1. Okay, so the magnitude of a is less than 1. Okay, so what if it was a matrix? So remember, our problem here was that we're summing something, and we are raising a matrix to the power of I minus 1. I was just doing it with the scalars here. So let's do it with a matrix. So what if I had the sum of I is equal to 1 to going to infinity of a to the power of I minus 1? That becomes I, so 1 minus a becomes identity matrix minus a raised to the power of minus 1 if all eigenvalues of this quantity are less than. So that's going to converge to the inverse of I minus a. Okay, so now let's go back to our problem. What were we trying to do? So we had this equation that said my W at the end of my learning is the following. This is what we had. Okay, so if this term A, this matrix, which is eta x transpose x, if its eigenvalues are all less than 1, then this term here being raised to infinity, this is going to go to 0. This is all going to be less than 1. Okay, so now the interesting term is this first term here. And based on the geometric series that we just found the answer to, what we think is that what this means is that this is equal to I minus the quantity that's inside the parentheses, which is I plus eta x transpose x minus 1 times eta x transpose y. Okay, so this is beautiful. Look what happens here. I have eta x transpose x minus 1 times eta x transpose y, which becomes x transpose x minus 1 x transpose y. So the W that we find with gradient descent, if we use the local derivative, is converging to the normal equation. So steepest descent converges to the normal equation and finds the minimum of the hill. Any questions about this? All right. I want to end today telling you a little bit about history. What did we just do? So we were using derivatives. What are derivatives? So I want to tell you about the invention of derivatives by Isaac Newton. And this goes to the 17th and 18th century. And we know about it from the work of Newton in this book, Optics, which was published in 1704. And he included two papers that basically established the concept of derivatives. And I want to just give you a sense of what was the idea behind using derivatives. So he started working on this thing in 1665, and also the story has something to do with the nature of science, which is often competitive. So here's the problem that Newton was working on. So suppose we know the distance x of t. So we know position of something x at time t, and we know it for various times. So we know this function x at various times t that represents position. So he wants to know, how do we find velocity? And it's obvious that velocity has something to do with the change in position over some time. And so he wants to know, how do I find that concept of change? So he says, suppose that x of t, this position here, is a function t cubed. So it's in this case it's a something that's rapidly moving forward, and in this case t cubed is the function that describes it. So that's the distance now, or the position of this particle, let's say. And what we want to know is that how much is its velocity. And so velocity is the idea of that if you take x at time t plus delta and you compare it to t x at time t and you divided it by the time delta, that would be its velocity, right? So how do we do that? And so he says, well, let's compute x at t plus delta minus x at time t. Well, if x is t cubed, then that's just t plus delta cubed minus t cubed. And so if I were to cube this function, I get t cubed plus 3t squared delta plus 3t delta squared plus delta cubed minus t cubed. So t cubes cancel out, and I get 3t squared delta plus 3t delta squared plus delta cubed. And he says, well, if delta is very small, we can ignore delta squared and delta cubed. We can ignore them because they're going to be, tiny, much tinier than something that's multiplied by t. So then distance traveled x t plus delta minus x of t is pretty close to 3t squared times delta. Okay, if that's the distance that's traveled, then the velocity is going to be that's 3t squared, right? So now we see, okay, I have the derivative of my function. So t cubed, its derivative with respect to time, becomes 3t squared. So Newton called this fluxion of x of t, and we now call it the derivative. So what was actually interesting is that he tried to, so in 1671, so he's written this, and back then there were no journals that you could submit things to. So he wrote it as he had a couple of papers and he wrote it in a book, and he tried to publish it. But as you can imagine, no bookseller wanted to publish a paper or a series of papers to describe the concept of a derivative, because he thought they thought nobody would buy it. So he couldn't publish it. So, but a copy of his work found its way to Leibniz, and Leibniz read it. He had similar thoughts about this, and so in 1684, this guy Leibniz publishes his book. He finds a publisher that he can use that describes the concept of derivatives. So it becomes a controversy between Newton and Leibniz about this, because Leibniz doesn't give any credit to Newton about this, and there's a this becomes a problem. And so when Newton publishes his book, Leibniz reviews Newton's book, writes a review of it, saying that this was taken from Leibniz's work. And so there's this controversy. And we now, the scholars think that they both came up with the concept of derivative independently, but Newton just couldn't publish his. And of course, what we know, the difference between what Newton and Leibniz is that Newton actually used the concept of derivative to make up the laws, the laws of physics, to describe motion of planets, which is not something that Leibniz had done. So even from the origin of science, we had these controversies about primacy of ideas. Okay, that is our story for today. Any questions that I can help answer for you guys? Hope you're having fun with the snow. Enjoy your time. Stay safe, and I hope to see you soon in person.